Hello, dear students. Welcome to session 7 of Math 204, offered to business informatics students in semester 2. In this session, we are going to discuss the determinants. We have just discussed the inverse, getting the inverse in the last session using the Gauss-Jordan method or algorithm, where we set an augmented matrix with the matrix that we need to get its inverse with the identity matrix of the same size, and then using the elementary row operations, we were transferring this side of the matrix to the other side, or formulating the identity matrix in the in the left-hand side, and we said that the constructed part of the matrix in the right-hand side will be the inverse of the matrix. And in this inverse now, this inverse of a matrix, or being able to commuting an inverse of a matrix, made us able to apply the division operation with matrices. Another property for matrices is the determinants. Let's discuss what is the determinants. What is the determinant? Why do we need the determinant, and how to get it? First of all, what is the determinant? It's a scalar quantity for the matrix. What for, or why do we need it? It indicates, the type of solution for linear system of equations. Also, it will help us in a different technique in finding the inverse of a matrix. And actually, it has a wide usage. These are two basic usage of the determinant in which we are going to use. So it's a scalar quantity for any n by n matrix. What does it mean, n by n matrix? It means that it's a square matrix where the number of rows is the same as the number of columns. So we are going to deduce a scalar matrix, a scalar quantity from a matrix, indicating its determinant to help us in solving linear system of equations, and to tell us more about the behavior of the system or the type of its solution, as well as in getting the inverse. How can we do this? If we said now that it's a scalar quantity for every squared matrix. Squared matrix, which is n by n. Let's start with the first order. If n is equal to 1, and this is the first size, we will have, for example, the matrix A with only one element, right? The determinant of this matrix will be denoted by det of A, like stated here, or the A with double bars, exactly like the absolute, like we do with the scalars, the absolute values, or we can simply write that A without brackets on the matrix letter. So the determinant here is, of course, exactly the same value. There's no elements to apply operations. Moving to the next size, enlarging the matrix. If we are working only in n by n matrix, so the next size is n equals to 2. If we have 1, 4, 5, 3, if this is B, deducing its determinant will be as follows. It will be the product of this main diagonal element, which means it will be 1 by 3 minus 4 times 5. So 1 times 3 minus 4 times 5. 1 times 3, of course, 3 minus 20, which means negative 17. Here is the scalar quantity, which is the determinant of that matrix. Let's enlarge the size one more time, and if n is equal to 3, let's say we will have this matrix from our worksheet. And we need to find the determinant. By the way, we can indicate that we are commuting the determinant just by writing the two absolute bars over the matrix itself. So we can write these two absolute bars on the letter of which denoting the matrix, or in the matrix itself. Now, when I say equal, we expect here the determinant, which is a scalar quantity, right? How can we do it with a 3 by 3 matrix? Actually, we will get any row or any column. We can use any row or any column to do the following. Let's first use row 1. We will multiply every element of the row. Here it's 0 times the determinant of the matrix, which doesn't include the row where the 0 exists, nor the column where the 0 exists. Again, we will remove the row where the 0 exists and the column where the 0 exists, which means we will remove this row and the first column, right? We will be left with this small 2 by 2 matrix, which is called the cofactor of 0. This is how we will call it. It will be -2, 0, 0, and -1. And we will get its determinant. And then minus the second element, which is -1, times what? Times its cofactor. Again, how to get the cofactor? We will remove the column which include the element -1 and remove the row which include that element as well. What is the left elements? If you remove this one and that one, what is the left elements? Yes, 4 and 0, 1 and -1. Let's write it here. And we will get the determinants. Finally, the last element, which is 2, times its cofactor. This is the cofactor of, if we called this matrix C, capital C, so this is the cofactor of small c of which element? 1, 1, right? Because it's the element in row 1, column 1. So we denote it by small letter c with suffix 1, 1. Or the submatrix. It's sometimes called submatrix or the cofactor. And also, I want you to take care of the sign. So the first element, we multiplied by its cofactor using the positive sign here. And then we multiply the second element by its cofactor times negative. And the last element with its cofactor, we didn't write the cofactor of 2, which is C what? Okay. This 2 is C. We are still in the first row, third column, so it's C1, 3. Yes. This matrix is called the cofactor of C1, 1. Okay, so it's 2 times what? Let's eliminate the row and the column where 2 exists. Eliminate that column where 2 exists. Eliminate that column where the row and column where 2 exist. We will just eliminate, we will just imagine that we have eliminated it. We don't have to erase it, of course. What's left, if we remove this part and that one, we will be left with these elements, 4, -2, 1, and 0. Then let's commute this value. The determinant of a 2 by 2 matrix, like we did before, here it's the product of the main diagonal elements minus the product of the off-diagonal elements, the elements which are out of the diagonal. So we have here 0 times whatever, of course it's 0, minus -1, we can say it's positive. What's the determinant of that matrix? It's 4 times -1, which means it's -4, minus, don't forget it's minus 0 times 1, which is 0, which means that we have here -4, yes, and then plus 2. The determinant here is 4 times 0, which is 0, minus this off-diagonal elements product, which is minus -2. Here we have plus 2. 2 times 2 is 4. And here we said it's -4. The determinant is equal to 0. Actually, when the determinant of a matrix is equal to 0, this indicates something about its inverse. We said in answering the question of why do we use or why do we need these determinants, what they are used for, we said that we are going to use them in solving linear system of equations and in finding inverse matrix as well. So if the determinant is equal to 0, it has something to tell about the inverse of a matrix. I will write it here. If A is invertible, which means it's not singular, it has an inverse A to the -1. This means that, or this implies that, inverse A is not equal to 0. If A has an inverse, and we call it invertible at that case, this means that its determinant, sorry, I want to write here the determinant of A is not equal to 0. Here the determinant is equal to 0, which means what? That is not invertible, which we call it singular. So here the matrix has no inverse. This means that C is singular matrix, or it has no inverse. Let's move to another exercise. Let me eliminate this part. Of course, we can increase the size of any matrix. We can increase the size to get the determinant of a 4 by 4 matrix. And we will do exactly the same. We will use any row or any column. For example, here we might have used the last row. And again, we will take care of the sign. From what we wrote here, it seems that the determinant of A is equal to what? Is equal to A11 times the cofactor of A, right? Or we can say it's the determinant of A11 plus A12, this element where we are calling here C, times the determinant of A12 plus A13 times the determinant of A13, which seems that this was minus. Let me write it with a different color here. So we had a positive product in addition to a negative product, in addition to a positive product. It seems that the sign is alternating. Actually, the definition, if we looked for the definition, we will find that it starts with -1 power n, if we wrote it with the sum of, because it's the summation of different products. Summation is denoted by the sigma notation, which is the sum of, if you were not introduced to it before, multiplied by A1. J1 is fixed, and then J is the counter here. So let's start here, J from 1 up till 3, multiplied by the determinant of Aij, which is 1 here. For 1, for example, instead of using the definition every time and deducing the -1 to the power I plus j, where I is the position of the row or the row index and j is the column index, instead of doing this, we can just go in order like positive, negative, positive, negative, positive, negative, positive, negative, positive. So if you need to use the second row, you can use it if its numbers were more simple. For example, here this 0 reduced the number of operations. If you have 2 zeros in a certain column or row, you may use it and get the benefit of simple operations, but take care of the sign. Here for that element, its position is row 2, column 2. So here we will have 2 plus 2, which is 4. 4, if we raise it to, as a power to -1, will eliminate the sign. So the sign of this element is 1. You can apply this to higher degree matrices in order to make sure that you didn't get the sign by mistake. This element is 2, 3, right? It's in row 2, column 3. If you add 2 plus 3, this is 5. It keeps the sign. And this is why it carries the negative sign. That element, the last example, it's the row 3, column 2. 3 plus 2 is 5. Again, it keeps the sign. For the 3 by 3, it's obvious, positive, positive, and then again, negative, positive, and so on. If it's 4 by 4, take care of the sign because it will be positive, negative, and then negative, positive, and so on because here the position will be 2 and 1, row 2 and 1. So here we will have an odd number which will keep the sign. So the negative at the last element in the first row will get here another negative following it. This is in the case of the 4 by 4 matrix. I want you to exercise it in the worksheet. So we might have used the second row instead of the first one, and we will take care of the sign. We will have here negative, positive, negative, and change the minors of each element. Let's say some properties, discuss some properties of the determinants. And as well solve more exercises. We have already now solved or answered the question what and why and how as well. Well, the properties are the first thing which we can think of. What if we need to get the determinant of an identity matrix? Actually, if you try to get the identity of any, the determinant of any identity matrix, it will be exactly 1. Also, the determinant of A transpose is the same as the determinant of A. If you found out the determinant of a certain matrix, so you might know that the determinant of its transpose is exactly the same number, so you don't have to repeat the operations. Also, it's beneficial to know that the determinant of A inverse is the inverse of determinant of A, which means we can write 1 over the determinant of A. So if you need the determinant of A inverse, you don't have to get the inverse and then find the determinant. No, just find the determinant of A, which is more simple operations than finding the inverse, and then get its reciprocal. Also, if we have a multiplication of 2 matrices inside the determinant, we can say that this is equal to the determinant of the products is the product of determinants. So as if we are distributing the determinant over the product. What about the addition? Unfortunately, it cannot be distributed in the addition, which means that the determinant of the sum of A plus B is not equal to the sum of the determinant of A and B. Another more property, if we need to find the determinant, I can use the absolute or this 3 letters det multiplied by a constant. It will be equal to C to the power of n times the determinant of A. And let's have a good idea let's discuss more these properties. Here I can say that the determinant of In is 1, and the C times A determinant is C to the power of NA, because I will need this space Okay. Let's discuss this exercise. Find the value of the determinant of each of the following. I choose part B. Use your result to state whether each of the matrices is invertible or not. Let's get the determinant of this matrix, and hence we can tell about its inverse, whether it exists or not. How to get the determinant? It's a 3 by 3 matrix. Yes, so we can use any row or any column. Let's repeat the operations. We may use the first row. We have 0, -1, and 2. We may use as well the last row because we have here 1, 0, and -1, which is more simple numbers. Okay, let's indicate the signs before we work. Write it with your pencil beside. So we have positive, negative, positive, negative, positive, negative. So it's positive, negative, positive, and the determinant will be deduced as 1 times its minor, right? Minus 0 times its cofactor, and then plus the -1 plus this -1 times its minor. Let's get the minors by removing the row in the column of the element, which is 1. We are left here with -1, 2, -2, and 0. Okay, remove now the column and row of that 0. We are left with 0, 4, 2, and 0. Finally, remove the column and row of the element -1. We will be left with these elements, which are 0, -1, 4, and -2. Let's find the determinant. Here we have 0 product, and then we have -4 multiplied by 1. 0 times whatever is 0, and here we have 0 minus -4, which is 4 times -1 is what? This is 0, -4, and -4, this is +4, which means that the determinant is 0. We found that the determinant of this 3 by 3 matrix is 0. And what does it tell, finally, about the inverse of that matrix? It tells that this matrix is singular, which means it doesn't have an inverse. It's not invertible. Fine. Let's move to the second question, the following one. Here we are asked to find the determinant of the product A times B. We are given the two matrices, A and B, of course, by two different methods, and then find the determinant of A inverse. Okay. Let's solve part B. We need to find the determinant of A times B. What do we have to get first? The determinant? No, of course, the product. Let's get the product of A times B. And we know that multiplying two matrices, we have to apply the check first. 2 is what? 3 by 3. So it's a 3 by 3 matrix. B is, again, 3 by 3. So we know that the product will be a matrix of which size? The outer dimensions, which are 3 by 3. Let's get it. The first row with the first column, this is 0 times -1 plus, which is 0. -6 times 3, which is -18. -1.5 times -2, which is +3. -18 plus 3, this is -15. And we will construct the whole matrix. Continue this operation. We will have here -3, -16.5, 10, 2, 12, 0, 0, 1. Okay, this is the product. Can we get the determinant? Yes, actually, simply we can use which row or column? We said we can use a row or column, it seems that the last row here is of the simplest numbers, right? Because if we need to get the determinant of A times B, we will say it's 0 times its cofactor, which is 0, minus 0 times its cofactor, which is 0, and finally plus 1. So 0 times its cofactor minus 0 times its cofactor. Let's get the cofactor. It's a good exercise. Removing the column and the row of that element, we will be left with what? Negative 3, negative 16.5, and 2 and 12. Removing the row and column of this element, we will get negative 15, 10, negative 16.5, and 12, exactly. Finally, plus 1 times its cofactor, remove the column and row, we will be left with negative 15, negative 3, 10, and 2. These two will be eliminated, so this 0, we remove the column and row, we are left with these elements here. For that element cofactor, we remove the column and row, we are left with these elements. Finally, for the 1 plus 1, we remove the column and row, and we are left with these elements. Okay. Sorry. We have the sign. Take care of the sign. It's positive, negative, positive, because if you went from the first element, positive, negative, positive, it will be negative, positive, negative, and then positive, negative, positive again. If we calculated the determinant of this product, it will be 0, 0. If we need to find the determinant of this product by a different method, which of these properties can we use? If we have property number 1, which is the simplest one, actually, and then number 2 here, and then number 3, 4, 5, and 6. Which property tells something about the product or the multiplication? Yes, it's number 5. So we can commute the determinant of this product, or we will say or. The determinant of the product AB can be deduced by the multiplying the determinant of A by the determinant of B. So first we can get the determinant of A using the matrix itself, which will be here. The determinant of A is 0 times the determinant of B, which we will not need to deduce because any product of 0 is 0. So the determinant of A, the product AB, is equal to 0, again with a different path or a different method. What does this tell about the inverse if we need to find the last requirement in this problem, which is the determinant of A inverse? How can we get it? The determinant of A inverse, we said that using these properties that were discussed in the lecture, we don't need to get the inverse. We will say that it's the inverse of the determinant of A. The inverse of the determinant of A, which means we can say it's 1 over the determinant of A. What was the determinant of A here? The determinant of A was 0. So does A has an inverse, has a determinant? We will say that A has no inverse. Why? Since the determinant of A was equal to 0, and hence there is no determinant of A inverse. But just we have to illustrate that the determinant of A inverse is the same as the inverse of the determinant of A. This is using the property or axiom number 5, which we can read it in that form, and then it does not exist because the determinant of A was 0, which means that from the beginning A is a singular matrix which has no inverse. Let's move to a different exercise to discuss more about the determinants. This is a completely different exercise. We are given here the determinant of a matrix A. It's given. And then we are asked to find the determinant of other matrices where there is an elementary row operation that happened. What does that mean? Here, given this A matrix, its determinant is set to 4. It's given. We need to find the determinant of that B matrix. This B matrix is deduced from the A matrix after what? This is the matrix. Let's observe the elements: 0, negative 6, negative 1, 2, 4, 0, negative 2, 0, 1. Fine. B is 2, 4, 0, which means the second row moved to the first row. This elementary row, the valid elementary row operation, is the exchanging of the two rows, right? We exchanged here in B. They exchanged which row? The first one with the second one. How would this affect the determinant? We would extend this properties list and see the effect of the elementary row operations. The first one is the exchange. The exchange introduced a negative sign. The second elementary row operation, which is multiplying by non-zero constant, K, for example, it will be multiplied by K. The last elementary row operations was adding two rows or two columns, adding or multiples of them, adding rows. This will have no change in the determinant. Now we are discussing how the determinants change with applying different elementary row operations. So if we have a matrix and we know its determinant, if we applied one of the elementary row operations, if we exchange two rows or two columns, this will add a negative. So now we know the determinant of B because it was deduced from A after exchanging the first two rows. We can directly know the determinant by adding negative sign. So here the determinant is simply negative 4. Exchanging any row would affect the determinant by a negative sign. Of course, you can try this to convince yourself at the beginning. You can get the determinant with the usual, here the determinant is 4. You can get the determinant here with the usual method. You will find that it's negative 4. So directly we can use this property. The second matrix, C, actually, it's very easy. It's telling us the operation which happened. We don't even have to observe it. So it's row 2. We multiplied it by 1/2. Here, the row 2, this was A. We multiplied here by 1/2, so we got 1, 2, and 0. And multiplying by any non-zero constant K, it will appear in the determinant. So the determinant of C will be that one times 1/2, which will be what? Yes, 2. Exactly. So the first valid elementary row operation, exchanging two rows or two columns, it affects the determinant with a negative sign, multiplying with non-zero constant. It multiplies the non-zero constant with the determinant value. Adding two rows, actually it has no change. So in matrix D, where it was deduced from the A matrix, that one, which is given here as well, by adding row 2 to row 1 and put the sum or the result in row 1, adding row 2 plus 1, 2 minus 2 is 0, 0 plus 4 is 4. The result is added to row 1, 1 plus 2, 4 minus 6, this is negative 2, and it's added here, and then 0 plus negative 1, this is negative 1, and then 2 plus 0, this is 2. This is what happened here. It tells us the question, the operation that happened, and as long as it is an addition, so we can say that the determinant of D here is what? Is exactly the same as 4. And here the determinant of B was negative 4 because we exchanged 2 rows, right? Okay, let's move to another question. Here it's another nice property of matrices. Let's keep this, these notes. If we have a triangular matrix, we have talked about this before. When we were introducing the matrices, we said that if the triangle, the below triangle to the main diagonal elements is zeros, we call this matrix a triangular matrix. Either this triangle of zeros is below diagonal or above. Here it's called lower triangular matrix because the elements are below the diagonal. Here it's upper triangular matrix because the elements are above the main diagonal elements. Here it's diagonal matrix. Why? Because we have zeros above and below the diagonal. We have only the diagonal elements, and all the off-diagonal elements are set to 0. These matrices are special cases. Their determinant is the product of the main diagonal elements. Here, for example, if we need to get the determinant of A, you will find that it's the product of the main diagonal elements. 2 times negative 2, negative 4, times 1, negative 4, times 3 is negative 12. And then for that diagonal matrix, it will be negative 1 times 3. Multiplying here, it will be negative 1 times 3, negative 3 times negative 2, negative 6 times 4 is 8, times negative 2 is 48. Okay. Here we need to find the value of the determinant of each of the following matrices using Saris. Saris is a different method in finding the determinant of a matrix, which is very interesting as well. This is the Saris rule. What does this rule says? It asks us to repeat the first 2 columns. So we will repeat the first 2 columns here, and we will get a matrix of that form. What we are going to do is, actually this was our matrix. What are we going to do is we are going to get the products of the diagonal elements, these diagonal elements as well, and these diagonal elements. We will get the products, 0 times whatever, this is 0, 0 times whatever, 0, 0 times whatever, 0, and we find the sum. And then we do the same with the opposite direction, starting from this one and get that diagonal. This product is 4. Here it's 0. Finally here it's negative 4. So we get 0. And what we do is we take this lower sum of products and subtract it minus the upper sum of products, and we will get the determinant. Therefore, here the determinant of A is equal to 0. But this is its mechanism. I wanted to do exactly the same steps here. Let's do it fast. We can remove this. Okay. Okay, add these two columns, 5, 1, 2. Here, -3, 0, -1. If you have 4 by 4 matrix, we said the determinants are dealing with squared matrices only. So if we have 4 by 4, we will have to add 3. It's the n minus 1. The n minus 1. Here, the n is 3. Because the n, the matrix which is n by n, the n was 3, so we add only 3. Now let's get the product of these diagonals. Here it's 0, here it's -12, and 0, and -2. Apply the addition. Get the product of the others. Of course, it returns to you which methods you need to use. We will have here 0 and -10, and here -9, so it's -19, and here we have -14. Take -14 minus -19, which is an addition. So -14 minus -19, this is 5, which means that 5 is the determinant of B. The last thing is the some other interesting information, the 0 determinant. We can know that the given determinant is equal to 0 at once if we notice 3 observations. Let me write the 0 determinants. First, if we have 0 row or column, so if we have the matrix of that form, the determinant here is what? It's 0 directly, because the row is 0. If we have 0 column, then the determinant is 0 as well. The second case, if we have multiples, the determinant of such matrix is 0. Why? Because row 2 is a multiple of row 1. The third case, I will write it here, if we have identical row or column. Here we have 2 identical columns, the first and the last, so the determinant here is equal to 0. That was all we needed for the determinants. Thank you very much for watching. Please study well. If you have any question, ask me on our group on Facebook. Stay safe. Till then, thank you and goodbye.